Thermal energy, temperature, and heat. In this lesson, we're going to be covering thermal energy versus temperature, heat and heat transfer, conduction, convection, radiation, specific heat capacity, and then the quantity of heat gained or lost, otherwise known as Q. Thermal energy versus temperature. Thermal energy is the total energy of a substance, so it's EK plus its EG. More mass or temperature means more thermal energy. So if it's more massive or it's moving faster, you're going to get a higher amount of thermal energy. Temperature is a measure of the average kinetic energy, so that's going to be more or less the speed and the mass of the atoms or molecules of a substance. So if the particle motion increases, temperature is going to increase. And if left together long enough, temperature between two substances will equal out. You're going to get the heat energy moving from one place to another. So if this is substance 1 and this is substance 2, eventually the heat energy from substance 2 will move to substance 1 and the speeds will equal out. Now similarly on the same document, you could say that substance 2 has a higher temperature than substance 1 because its particles are moving faster. Check your understanding. If you have two samples of water, each at 100 degrees Celsius, but sample A contains 1 kilogram of water and sample B contains 2 kilograms of water, which sample's molecules have higher average kinetic energy? What does this value represent? And B, which sample has greater thermal energy and why? Check your understanding. You have two samples of water, each at 100 degrees Celsius, but sample A contains 1 kilogram of water and sample B contains 2 kilograms of water. So 2 kilograms, 1 kilogram, and they're both at 100 degrees Celsius. Remember, 100 degrees Celsius is going to represent the temperature, and that's going to equal to the movement of the individual molecules. So A says, which sample's molecules have a higher average kinetic energy? And what does this value represent? Well, average kinetic energy per molecule is going to be based on the speed. Higher speed is going to equal an increase in EK average per molecule. Now, since both sets of molecules are at 100 degrees Celsius, we're going to say that the EK average for A is going to equal to the EK average for B, because we're talking per molecule. So even though there's more molecules in B, the average speed per molecule, the average kinetic energy per molecule is going to be the same between both substances. Now, what does this value represent? Well, we just mentioned that it's going to represent the speed and the energy available per molecule. B asks, what sample has a greater thermal energy? Well, thermal energy is going to equal to the total EK, so total, plus EG, total, per substance. If we take a look at the thermal energy for A versus the thermal energy for B, the difference lies in the mass. There's more mass in B. Since there's more mass in B, we're going to get a higher EK total and a higher EG total. So we can say that the energy thermal in A is less than the energy thermal in B, because B has 2 kilograms, therefore it has more mass, therefore it's going to have a higher EK and a higher EG. Check your understanding. If you have two samples of water and each has a mass of 1 kilogram, so we're going to say A and B, and they're both going to be 1 kilogram. Sample A has a temperature of 100 degrees Celsius, and sample B has a temperature of 50 degrees Celsius. A asks, which sample's molecules have higher average kinetic energy? Well, remember, that is based on the speed of the molecules, and since we're talking about per molecule, it doesn't matter about the mass. Now, both have the same mass, so all we're really looking at is temperature. Now, since the temperature of A is bigger than the temperature of B, then we would say that A's molecules have a higher or greater average kinetic energy than B, because they have a higher temperature. B, which sample's particles have a greater motion? Well, motion is going to be tied directly to temperature. We can say that the temperature of A is greater than the temperature of B. Therefore, the motion of A is greater than the motion of B. And C, which sample has a greater thermal energy? Well, thermal energy is going to be based on both the EK and the EG. Now, these two variables depend both on the velocity and the mass. Now, since the masses are equal to each other, the differentiating factor is going to be the velocity. Since we know the velocity of A is bigger than the velocity of B, we can say that the thermal energy of A is greater than the thermal energy of B. Thermal energy versus temperature versus heat. So what do these three things mean? How are they different from each other? Well, the thermal energy is the total energy of a substance. We just talked about it as the EK and the EG. Temperature is the measure of the average kinetic energy of the atoms or molecules of a substance, and heat is the energy which is transferred from one substance to another. So heat is not really a thing. Heat allows us to transfer energy from one place to another. So we take a look at our left picture here, and let's just say we put it on a hot plate. We're going to add energy to the system. Heat is the energy which is being transferred. So yeah, we're adding energy, but we're adding heat to the left picture here. As we add heat to the left picture, then that's going to drive the energy up, which is going to increase the temperature of the substance on the right. Heat. What is heat? Heat is energy, as we just talked about. Objects cannot possess heat, however. They can only possess energy. Heat is the thing that's transferred from one place to another, whereas energy is the thing that they're left with once the heat has been transferred. When heat is added to a system, energy is added to the atoms. This increases the thermal energy and the temperature. When heat is removed from a system, thermal energy and temperature decrease due to a loss of energy. So in this case, from left to right, we're going to increase temperature by adding heat. And as we go from right to left, we're going to decrease temperature as we remove heat from the system. Heat transfer. Heat moves from one system to another because of differences in system temperatures. If you have two objects, a hot and a cold object, heat is going to move from the hot to the cold, increasing the temperature and the average thermal energy of the cold particles. So if you have two different substances with equal temperatures, there'll be no flow of energy. If you have equal temperatures on both sides, energy is not going to flow back and forth. Heat is not going to flow back and forth. When you have two systems with different temperatures, the energy will flow from hot to cold. This isn't necessarily true, however, if you're going from a higher thermal energy to a lower thermal energy. As in, thermal energy is the EK plus EG total. So what does this mean? Well, we can have two different substances, A and B. But as you can see, there's way more content in B. If they have the exact same temperature, let's say 50 degrees Celsius, they're going to have an equal temperature, but we're going to have a lot more thermal energy here than here because there's more mass. So we're not going to get a movement of heat due to a difference of thermal energy. However, if instead of 50 degrees Celsius, if this guy was 100 degrees Celsius, then you will get a movement of heat from substance A to substance B. Now, how does this heat move? Well, it moves via conduction, convection, and radiation. So first up, conduction. Conduction is the transfer of heat through physical contact. The picture on the right shows how a metal handle is heated. If we're going to heat the contents inside the kettle, then the metal handle, will get hot through a process called conduction. Prolonged contact with the heat will increase the temperature, so the motion of the particles, and the thermal energy of the metal, causing it to become very hot. And we can also see this if we put a metal skewer or metal poker into a flame. Eventually that flame will heat up the metal and will make it very hot. And you can see how it's hot down here, and it's a little cold up here, but eventually that heat will make its way up the metal rod. Convection. Convection is the transfer of heat by the circulation of a heated fluid, so this can be a liquid or a gas. Particles of the fluid move around, carrying energy with them. And you can see inside our kettle here, you're going to get the movement of hot liquid up, which is going to drive that energy upwards. This hot fluid is less dense, causing it to rise, and the cold fluid to fall down, causing them to mix. And when the cold fluid comes down, it's going to become hot, and then it's going to rise back up. The thermal energy is transferred from the hot places, i.e. the warm air, to the cold places, the cold air, as the air is circulating around. And this happens a lot in ovens, home furnaces, kettles, fires. If you think about your home, we can draw a real quick sketch of your home. You're going to have your top floor, your middle floor, and then your basement. Well, where's the furnace located? Well, the furnace is located in the basement, because what it does is that it heats air in the basement, and that hot air is able to rise, and that hot air is able to go through different vents in the house, allowing the whole house to be heated using one furnace located in the basement. If that furnace was instead in the attic, then you wouldn't get very good heat circulation, and a lot of that heat would be lost outside. Radiation. Radiation is the transfer of heat via electromagnetic radiation, i.e. visible light, microwaves, and infrared. The sun transfers heat using all aspects of the EM spectrum. Other objects like people, rocks, etc. transfer thermal energy through infrared radiation. And you've all seen pictures like this on the bottom here. You can see how different parts of the guy are glowing, different colors, depending on the heat that he's giving off. And I really like this picture because you can see, even with a bag over his hand, you can still see his hand clearly in the picture on the right, because the infrared camera is actually just picking up the heat being emitted from the hand. Now the hand isn't quite as bright as everywhere else because some of that heat is being absorbed by the bag, but you can still see it clearly even though the bag is covering it. Now you can see other places like his face giving off a lot more heat. Pretty neat picture. Now another example of radiation is the energy that comes from the sun, and that's represented by this blue arrow here, and you can see how the energy from the sun radiates towards Earth. Now this is very important because radiation doesn't need a medium, so particles, to transfer energy. So this is unlike conduction and convection, which need a medium to transfer their energy. So they need air particles, they need water particles, they need metal particles, etc. Radiation does not need this medium, which is very important because that means that the radiation, the heat energy, can travel from the sun to the Earth in outer space. So here's an overview of our three different methods of heat transfer. So you're going to have conduction, which is transfer of heat through touch, convection, which is the transfer of heat through the movement of gas and water particles, and radiation, which is the transfer of heat through different parts of the EM spectrum. Check your understanding. I'd like you to answer the following questions using terms learned from this lesson. So I'm going to read through the 5 questions, then you're going to pause the video, answer them, and then we're going to come back and have a look at the answers. Number 1, why would putting a metal skewer into a potato decrease cooking time? So what do I mean by that? Well, there's our potato, and our metal skewer is just a piece of metal that goes into the inside of the potato. Number 2, why do clothes irons have plastic handles? Number 3, why does smoke rise up the chimney? Number 4, why is the floor the best place to put a heater? And number 5, Why can conduction and convection not occur in space? So pause the video and answer these 5 questions. Okay, so number 1. So what the skewer would do, it would heat up via convection and then it would transfer that heat via conduction. So if we draw our potato again and our skewer, typically our potato is going to be heated from the outside in, like that, right? But if we heat the skewer, and we make the skewer really, really hot, well then the skewer is going to be able to cook the potato from the inside out. This is going to allow us to heat our potato faster. Number 2, if the handle of the closed iron were metal, you can imagine it would get really, really hot. And it would get hot via conduction. Number 3, hot air rises because it gains thermal energy as the particles start to move faster, so an increase in temperature. As they move faster, they spread apart, decreasing their density. Lower density, hot air rises up the chimney. Number 4, why is the floor the best place to put a heater? Well, that's because hot air rises, like we were just talking about. If we were put on the ceiling or in the attic of your house, like we were talking about before with the furnace, then most of the air would either stay there or be lost to the outside. And number 5, conduction and convection require a medium to travel through. Space does not have any particles or very, very few particles, so we require radiation to get heat from the sun to the earth. Calculating heat transfer, specific heat capacity. Different substances hold heat differently. For instance, water molecules hold heat better than steel molecules, and therefore heat is transferred much faster in steel than in water. Specific heat capacity, C, is a measure of the amount of energy, joules, needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. So for example, the C of water is 4.18 times 10 to the 3 joules per kilogram degree Celsius, which means that it takes 4.18 times 10 to the 3 joules of energy to increase the temperature of 1 kilogram of water by 1 degree Celsius. This also means that if you lower the temperature of 1 kilogram of water by 1 degree Celsius, you're going to release 4.18 times 10 to the 3 joules of energy. Quantity of heat gained or lost, Q. Q is the amount of heat gained or lost by a body, and it's equal to mc delta T. M is going to be mass in kilograms, C is going to be our specific heat capacity that we just talked about in joules per kilogram times degrees Celsius, and T is going to be our change in temperature in degrees Celsius. Q is a measure of the heat energy, therefore the units are in joules. Check your understanding. How much heat is needed to raise the temperature of 2.2 kilograms of water with a C of 4.18 times 10 to the 3 joules per kilogram times degrees Celsius from 20 degrees Celsius to the boiling point? So give your answer in megajoules. So first of all, let's write down what we have. So we have mass is equal to 2.2 kilograms. C is going to equal to 4.18 times 10 to the 3. Our change in temperature is going to be 80 degrees Celsius because we're going to go from 20 degrees Celsius to 100 degrees Celsius. So we get 80 degree difference. So let's calculate Q. Q is going to equal to M, which is 2.2, times C, which is 4.18, times 10 to the 3, times 80, our delta T. And that equals to 735,680 joules. And you're going to get 1 million joules per megajoule. So when we're dividing by a million, we're going to move our decimal to the left 6 times. So 1, 2, 3, 4, 5, 6. And we're going to get 0.735680 megajoules. We need 2 sig digs for our answer, so we're going to get 7.4 times 10 to the negative 1 megajoules. Here are some specific heat capacities you'll be using. So glass, 8.4 times 10 to the 2, iron, 4.5 times 10 to the 2, and then water, 4.18 times 10 to the 3. You can see it's already 10 times higher. So it holds on to its energy 10 times more than iron does, and alcohol is somewhere in the middle between the iron and the water. The principle of heat exchange. When heat is transferred from one system to another, the amount of heat lost by the hot system equals the amount of heat gained by the cold system. Therefore, Q lost equals Q gained, or Q lost plus Q gained equals 0. Heat energy will continue to flow to the colder system until both systems have equal temperatures. So let's have a look at what this could mean. Check your understanding. A 200-gram piece of iron at 350 degrees Celsius is placed in 300 grams of 10 degrees Celsius water to be cooled quickly. So we'll say iron, water, the mass of iron is 0.2. The mass of water is 0.3. Remember, we got to use kilograms. We'll say Ti for the iron is 350 degrees Celsius, and Ti for the water is 10 degrees Celsius. So note, number 1, Tf for water and iron will equal because the heat's going to move back and forth until the temperatures are the same. And number 2, the object that loses energy has a negative Q value. So the last variable we need to put in is our C values. So our C for iron is 4.5 times 10 to the 2, and our C for water is 4.18 times 10 to the 3. Q lost equals Q gain. And we just said the object that loses energy is going to have a negative Q value. So we're going to say negative Q lost equals Q gain. Now, which one's going to lose energy? Well, that's going to be our iron. Right? Iron is going to lose, and our water is going to gain because the energy is going to go from the iron, the hot iron, to the cold water. So we're going to have negative. So for our mass for iron is 0.2 times the C is 4.5 times 10 to the 2 times TF minus T initial, which is 350, bracket, equals Q gain, which is going to be the mass, 0.3 times 4.18 times 10 to the 3 times TF minus 10. Now we're going to expand them out and simplify as much as we can. So what is 0.2 times 4.5 times 10 to the 2? We're just going to tackle that part there. So we'll leave the negative on the outside, and we're left with 90 times TF minus 350 equals, now we're going to say 0.3 times 4.18 times 10 to the 3 equals 1254 times TF minus 10. So on the left-hand side, we're going to have minus 90 TF plus, you have 90 times 350, 31500 equals 1254 TF minus 1250, because we're just expanding the brackets out. Now we're going to collect like terms and we're going to simplify. So we're going to bring this guy over to there, we're going to bring that one over to there, and we'll be left with 44040 on the left and 1344 TF on the right. We're going to divide both sides by 1344, and we're going to get a TF value of 32.8 degrees Celsius, and then let's round it 2 sig digs. So we get a final TF value of 33 degrees Celsius. And that concludes our lesson on thermal energy, temperature, and heat.